Diodes have two modes of operation. One is forward bias, another is reverse bias. Diode is said to be in forward bias when its anode terminal is at a higher potential when compared to its cathode terminal. If anode is at a lower potential when compared to its cathode, then the diode is said to be under reverse bias. Under forward bias, diode conducts heavily, resulting in the flow of good amount of current. This large current is due to lowering of the height of potential barrier that exists at the junction region. Under reverse bias, the diode current is small but the same applied voltage, and this smaller lower current is due to the increase in the height of the potential barrier that exists in the junction region. The large current that flows under forward biased condition is associated with the phenomena diffusion, whereas the smaller current that exists in the diode under reverse biased condition is associated with the drift. Diffusion is a phenomena in which carriers move from one point to another due to the existence of carrier concentration gradient. It is a natural phenomenon where particles move from higher concentrated regions to lower concentrated regions. This is called diffusion. When diffusion exists in electrons or holes, diffusion current results. Drift is a phenomenon in which charged particles move from one point to another point when they are in a region where there exists potential gradient. When a charged particle is in a region where there exists potential gradient or electric field, it experiences a force. This force is called Coulomb's force. This force then accelerates the particles or particle moving from one point to another point. This movement results in current. That type of current is called drift current. Diffusion current is mainly located, concentrated to P region and N region in diodes, whereas drift current, it is limited to junction region in the diodes. Therefore, now we can understand under forward biased condition, diode exhibits smaller resistance, and under reverse biased condition, it exhibits higher resistance. One more point regarding currents in the diode is under forward bias, the voltage current relation is exponential, whereas under reverse bias, the current through the diode is voltage independent. As already mentioned, it is very small when compared to forward bias conditions. Diodes also exhibit two types of capacitances. Under forward biased condition, one capacitance, this is called storage capacitance. Another name is also there, diffusion capacitance. Quantity wise, it is large. Under reverse bias, the diode exhibits another type of capacitance. It is called transition capacitance. Another name is also there. It is depletion capacitance. Quantity wise, it is very small. Here, one point requires to be mentioned. Under both types of biased conditions, both types of capacitances exist. However, under forward bias, storage capacitance dominates, diffusion capacitance dominates, whereas under reverse bias, transition capacitance or depletion capacitance. Electronic devices, junction diodes, problems, series on semiconductor devices and circuits, lecture number 2.18. PN junction diodes are semiconductor devices, two-terminal devices. These are non-linear and unilateral, well known for their rectifying properties. They offer high resistance to current when it is in one direction and offer very low resistance when the current is in the opposite direction. Apart from this rectifying property, they also exhibit several interesting properties. In the present session, we consider several problems and their solutions, which are based on different interesting properties, characteristics of PN junction diodes. Before going further, we recollect the expression for dynamic resistance of junction diode. By definition, dynamic resistance is dV by di. It is usually indicated by small r. V stands for voltage across the diode, I stands for current through the diode. It is mentioned here that V to I ratio, it is called static resistance. dV by di is dynamic resistance. Now, this definition can be applied to Shockley-Diode equation to find dynamic resistance of diode. Diode equation or Shockley-Diode equation is I equal to I naught e power V by eta Vt minus 1. Differentiation both sides leads to di equal to I naught into e power V by eta Vt minus by eta Vt dV. With a little bit of manipulation leads us to get dV by di equal to eta Vt by I naught e power V by eta Vt. This is the expression. And this expression is valid both biased situations. But in case of forward bias, this can be simplified a little further. I naught e power V by eta Vt. This is from Shockley-Diode equation. This quantity can be seen as I plus I naught. This I naught can be brought to left side. It becomes I plus I naught. So R equal to eta Vt by I naught plus I. In case of forward biased situation, I naught is negligible when compared to I. Therefore, I naught can be neglected. Notice this neglect can be done only under forward biased condition. Once neglected, I naught plus I becomes simply I. So R equal to eta Vt by I. This is the relation in case of forward biased condition. So R here gives us diode resistance under forward biased condition. In case of reverse biased condition, no further simplification is possible from the ratio dV to di ratio which we got earlier. So R is eta Vt by I naught e power V by eta Vt. This is the resistance under reverse biased condition. Now we consider a problem. A diode carries a current of 0.5 milliamperes and 20 milliamperes when applied voltages are 400 millivolts, 500 millivolts respectively. Determine emissivity eta and the reverse saturation current. Two currents at two different voltages are given. From voltages and their corresponding currents, one can easily identify that these currents voltages belong to forward biased condition. Diode current is I equal to I naught e power V by eta Vt minus 1. Under forward biased condition, 1 or I naught can be neglected. So I equal to I naught e power V by eta Vt. From this, I2 by I1. I2 is current at voltage V2. I1 is current at voltage V1. I2 by I1 is I naught e power V2 by eta Vt divided by I naught e power V1 by eta Vt. From this relation, eta emissivity can be solved. It turns out to be V2 minus V1 by Vt natural logarithm I2 by I1. Substituting the given values, 500 minus 400 divided by 26. 26 is Vt, temperature equivalent of voltage or voltage equivalent of temperature, 26 millivolts at room temperature, into natural logarithm 20 by 0.5. It turns out to be 1.04. So emissivity eta is obtained and the reverse saturation current is also required to be determined. I equal to I naught e power v by eta Vt. In this, we can substitute values of current, values of voltage, values of eta Vt. It gives us I naught equal to 195 picoamperes. Another problem, a germanium diode is at room temperature. It is carrying 0.5 milliamperes under forward biased voltage of 400 millivolts. Determine diode current when temperature is raised by 10 degree centigrade. Work out the problem for silicon diode. The diode is germanium diode, so emissivity is 1, eta is 1. So one can write current at temperature T is equal to I naught e power V by Vt, as eta is 1 minus 1. I naught can be neglected, so this one can be neglected. So it is equal to I naught e power V by Vt. It is given that current is 0.5 milliamperes. Voltage is 400 millivolts. It is at room temperature, so Vt is 26 millivolts. Substituting all these values, we have this relation 0.5 equal to I naught e power 400 by 26. Now consider the temperature rise by 10 degrees. Vt at this raised temperature is 310 by 11,600. It turns out to be 26.72 milliamperes. So now we can consider the ratio of currents. I, diode current at T plus 10 by diode current at T. This ratio is 2 I naught e power 400 divided by 26.72 divided by I naught e power 400 by 26. Why it is a 26.72 in the numerator? Because Vt at raised temperature is 26.72. That's why this value. And then this Y2 here. Reason is reverse saturation current doubles for every 10 degree rise in temperature. Rise in temperature is 10 degrees. So if it was I naught earlier, after rising temperature, reverse saturation current becomes 2 I naught. Now I naught gets cancelled. We are left with a relation I of t plus 10 is equal to 0.5 to e power 400 by 26.72 by e power 400 by 26. It gives us a value 0.66 milliamperes. In case of silicon diode, eta equal to 2, then following procedure similar to what we followed just now. For germanium, we get the current at a raised temperature as 0.81 milliamperes. Another problem, problem 3. Assuming a forward current of 5 milliamperes, determine forward dynamic resistance of a silicon PN junction diode at a temperature of 200 degree Kelvin, 250 degree Kelvin, 300 degree Kelvin. Forward dynamic resistance is given by this formula, R equal to eta Vt by I. For silicon, eta is 2. Vt is T by 11,600. It varies with the temperature. It is given that forward current is 5 milliamperes. So I is given. So eta is known, I is known, Vt varies with the temperature. Substituting these values, dynamic resistance can be found without any difficulty. When temperature is 200 degree Kelvin, Vt is T by 11,600. It is equal to 200 by 11,600. It turns out to be 17 milliamperes. Substituting 17 milliamperes in this relation for Vt and 5 milliamperes for I2 for eta, one can get R as 6.8 ohms. Similarly, for 250 Kelvin, 300 Kelvin, also one can find dynamic resistance. It is 8.62 ohms at 250 Kelvin and 10.34 ohms at 300 Kelvin. Another problem: for determine the values of DC and AC resistances of germanium PN junction diode with a reverse saturation current of 0.5 milliampere at 200 Kelvin and also at 300 Kelvin, given that applied voltage is 200 millivolts. Solution: to begin with, determine Vt at 200 Kelvin. It is 17 millivolts. Current through the diode under forward biased condition. It can be determined from the Shockley diode equation. I equal to I naught e power v by eta Vt minus 1. One can be neglected here in this relation. Substituting the given values, one can find I as 64.31 milliamperes. Forward resistance. This is DC resistance, static resistance. It is usually indicated by RF, capital RF. It is applied voltage divided by resultant current. 200 by 64.31. It turns out to be 3.11 ohms. Now AC resistance. Dynamic resistance is eta Vt by I. Eta, it is germanium diode, therefore eta is 1. Vt already found 17 millivolts. I is already determined, it is 64.31 milliampere. Substituting, one can find R. It turns out to be 0.26 ohms. In the same manner, these two quantities, DC and AC resistances, can be determined at 300 Kelvin too. They turn out to be 13.42 ohms and 1.68 ohms. First one is forward DC resistance. Second one is forward AC resistance. Another problem, fifth one, determine forward and reverse dynamic resistances of a germanium junction diode when the applied voltage is 250 millivolts at 400 Kelvin, assuming a reverse saturation current of 5 milliamperes at room temperature. So here dynamic resistances both under forward and reverse biased conditions. Solution: first determine Vt at 400 Kelvin. 400 by 11,600 gives us 34 millivolts. And then determine reverse saturation current at 400 Kelvin. Reverse saturation current is given at a room temperature, that is 300 Kelvin. We need 400 Kelvin. To find it at 400 Kelvin, we use the relation that reverse saturation current doubles for every 10 rise in temperature. That relation's mathematical form is I naught reverse saturation current at 400 degrees is equal to reverse saturation current at 300 degrees multiplied by 2 power 400 minus 300 by 10. It gives us reverse saturation current 5.12 milliamperes at 400 Kelvin. Once Vt and I naught at 400 Kelvin is available, forward dynamic resistance, reverse dynamic resistance, both can be determined easily using the expression R equal to eta Vt by I naught e power v by eta Vt. Notice this expression is valid for both forward and reverse biased conditions. So substituting the available values, we can get R 4.25 milliohms. This is forward dynamic resistance. We get R as 10.36 kilo ohms. This is reverse dynamic resistance. Another problem, sixth problem, determine contact difference of potential at room temperature when Na, acceptor impurity concentration, is 1 into 10 power 11 per cm cube. Nd, donor impurity concentration, is 1 into 10 power 13 per cm cube, assuming intrinsic carrier concentration of 1 into 10 power 10 at room temperature. Also determine its value when temperature is doubled. Solution. Contact difference of potential V naught of T is Vt natural logarithm Na Nd by Ni square. This is the formula which we are going to use to determine contact difference of potential. Na is given, Nd is given, Ni is given. Substituting, we get 239 millivolts. Of course, Vt is volt equivalent of temperature. It is 26 millivolts at room temperature. When temperature is doubled, Vt gets doubled and Ni square becomes 8 times. Considering this aspect, V naught of T at doubled temperature, it is 2 into 26 natural logarithm 10 power 11 into 10 power 13 by 8 into 10 power 20. So it gives us contact difference of potential 585 millivolts. Before going further, one aspect is to be mentioned. Ni square also depends upon semiconductor gap voltage, which changes with the temperature. So change in temperature also causes change in gap voltage, which leads to change in intrinsic carrier concentration. That aspect is ignored in calculating contact difference of potential in this problem. Another problem, given the reverse saturation current of a germanium PN junction diode is 20 milliamperes at room temperature. Find reverse saturation current of diode at a temperature of 75 degrees, 400 degrees Kelvin. This problem is set around the point that reverse saturation current doubles for every 10 degree rise in temperature. Mathematical form for that particular relation is I naught of T2 is equal to I naught of T1 into 2 power T2 minus T1 by. So I naught at 75 degrees is I naught at 25 degrees into 2 power 75 minus 25 by 10. It gives us 640 microamperes. Similarly, I naught at 400 degrees can be determined. It turns out to be 20.48 milliamperes. The reverse saturation current of germanium PN junction diode at a temperature 125 degree centigrade is 30 milliamperes. Assuming an applied voltage of 0.2 volts bias, determine dynamic resistance under A forward, B under reverse bias conditions at the same temperature. Work out the problem when the diode is made with silicon. Now solution. Vt is T by 11,600 and at 125 degrees centigrade, it is 125 plus 273 divided by 11,600. It turns out to be 34.31 millivolts. Now, dynamic resistance. The relation for dynamic resistance is eta Vt by I naught e power V by eta Vt. This is valid both for forward as well as reverse biased conditions. Under forward biased conditions, V is positive. Under reverse biased condition, V is negative. So substituting the available values, one can find R as 3.36 ohms. This is for germanium. Eta is considered as 1. Eta is considered as 1. In case of silicon, eta is 2. So 2 is considered. So forward biased resistance for silicon is 124 ohms. Reverse bias resistance for germanium. It is 388.95 kilo ohms. For silicon, it is 42.18 kilo ohms. Another problem, a germanium diode has a saturation current of 1 nanoampere at 20 degrees centigrade. When it is forward biased by 0.4 volt, determine the current. Also find the current when the temperature is raised to 110 degrees centigrade. Solution. First, determine Vt. Vt at 20 degrees centigrade. So 20 plus 273 by 11,600 is Vt. It turns out to be 25.25 millivolts. At 110 degrees centigrade, Vt turns out to be 33 millivolts. I is always I naught e power v by eta Vt minus 1. So substituting the given values, one can find I as 7.58. Now, this is the current when temperature is 20 degrees centigrade. When temperature is 110 degree centigrade, this is the relation. I can be found as 94 milliamperes. Reverse saturation current when temperature is raised can be determined from I naught at 110 degrees centigrade is 10 power minus 9 into 2 power 110 minus 20 by 10. It turns out to be 512 nanoamperes. Another problem, consider a germanium diode at room temperature with a reverse saturation current of 20 milliamperes. Determine the ratio of forward and reverse biased currents and static resistances when magnitude of bias is 0.08 volts. Solution. Simply consider the ratio of forward current by reverse current. Forward current is I naught into e power forward biased voltage ET divided by eta Vt. Germanium diode is given, so eta is 1. Room temperature means it is 26 millivolts. So this is forward current with I naught. Reverse current is I naught e power minus 80 by 26 minus 1. I naught gets cancelled. You are left with. Now this one can be calculated. It turns out to be minus 21 by 85. The reason for minus sign is IF, IR. They are in opposite directions. RF forward resistance, static resistance is V by IF. IF is found very easily. V is given, so it is 0.08 by 20 into e power 80 by 26 minus 1. It turns out to be 193 ohms. Reverse resistance, static resistance, it is V by IR. V is same 0.08. IR, reverse current, it can be determined from 20 into e power minus 80 by 26 minus 1. It turns out to be 4.21 kilo ohms. With this, we come to the end of this session. Let us recollect important aspects that are touched upon in this session. Several problems set around the properties of diodes, forward resistance, reverse resistance, reverse saturation current, static resistance, dynamic resistance, reverse saturation currents dependence on temperature. All are considered in this session. Hope this session is useful to you. We meet again in another session with a new topic soon.